Good morning. In the previous session, we have discussed about the elimination and addition reaction mechanisms under the types of organic reaction mechanism. In this session, we will have a discussion on substitution reactions. Substitution, a chemical reaction that occurs when one of the functional group in a chemical compound is replaced by another functional group. That means instead of an atom or group that is already found to present in the system, if a new atom or a group is introduced, that is called substitution reaction. Based on that attacking species, that means the group which is going to be introduced into that compound, the substitution reactions that can be classified into three types. One, if this incoming group, that means the attacking species that comes with the excess of electron, that is called nucleophilic substitution reactions. Suppose if the electron deficient species is the attacking species, then that is called electrophilic substitution reactions. If the radical is the attacking species, then the type of substitution reactions are called as radical substitution reactions. Now, the nucleophilic substitution reactions. A nucleophile is a chemical species with an unshared pair of electron. That means any species with excess of electron, that means electron richer species, are called as nucleophiles. The term philic means, that is a Greek word, philic means loving. So nucleophile means a nucleus loving or nucleus seeking species. So any nucleophile that can be a electron richer species, most often nucleophile are electron richer species. Some of the cases, even a neutral species like water can also be act as a nucleophile. Nucleophiles always have unshared pair of electron that forms a new chemical bond, but they are not always negatively charged. Aliphatic nucleophilic substitution reactions. Substitution reactions in terms of nucleophilic substitution means definitely this is meant for aliphatic substrates. Why this is means? Aliphatic substrates are more capable of forming the nucleus, that means a carbocationic type of intermediate can easily be formed in case of aliphatic substrate. Several distinct mechanisms are possible for aliphatic nucleophilic substitution reactions depending on the substrate, nucleophile, leaving group and reaction conditions. So nucleophilic substitution reactions that can further classified into three types. SN1, substitution nucleophilic unimolecular. The next one is the next major category, SN2, substitution nucleophilic bimolecular mechanism. There is a third category, that is substitution nucleophilic internally that occurs, that means SNI mechanism. Most of the nucleophilic substitution reactions that takes place either by SN1 or SN2, that means that mechanism may be a unimolecular mechanism or a bimolecular mechanism. We can distinguish that SN1 and SN2 mechanism by either using the stereochemistry and then at the reaction kinetics of that mechanism. Let's see the SN1 mechanism. As we have discussed earlier, aliphatic substrates are more capable of forming a carbocation type of intermediate. The unimolecular mechanism are always occurring in two steps. The substrate that undergoes ionization, thereby it forms a carbocation type of intermediate. Most often that unimolecular mechanism are said to be solvolysis. This is because solvent plays the major role in forming or stabilizing that carbocation. The first step is always the rate determining step, that means the ionization step is the rate determining step. The second step is attack by the nucleophile, that is the fast recombination step. Kinetic evidences for unimolecular mechanism. These reactions occurs in two steps that we have seen in the previous slide. The first step is the slow and rate determining step. Since the slow step involves the substrate concentration only, that means the rate of the reaction that purely depends on the concentration of substrate only. So the R is found to be unity and molecularity is also found to be unity. So rate directly proportional to the concentration of substrate only. So this is one of very important kinetic evidence for the reaction that occurs in a unimolecular pathway. The second major evidence that comes from the stereochemistry. In the previous slide, we have seen during the rate determining step, a carbocation is produced. That carbocation has a trigonal planar shape. So that incoming group in the second step that has to attack the carbocation. There are two possibilities that carbocation that can be attacked by the nucleophile either from the top or from the bottom. So equal possibilities are there, or equal probabilities are there. So that suppose if the starting material has a chiral carbon, means then the product definitely bound to be a DL isomer. That means the racemic mixer. So from the nature of the product that we can arrive at a conclusion whether that mechanism is unimolecular or not. The second mechanism, that is bimolecular mechanism, SN2 reaction mechanism. SN2 mechanism that occurs in just one step and has no designable intermediate, as we have seen in the SN1 mechanism. In this mechanism, the nucleophile, in the given example Br plus, that approaches that carbon which is bearing that nucleofuge, that means the leaving group, only from the back side. This is because that nucleofuge as well as the nucleophile are having the same charges. So electron repulsion are possible. Just to avoid that electron repulsion, the nucleophile Br minus that approaches that carbon bearing the leaving group only from the right side. So attack is always the right side attack in case of bimolecular mechanism. So if that nucleophile approaches the carbon which is bearing that departing group, that means the nucleofuge, then a partial bond between that carbon and the nucleophile is formed. At the same time, the bond between the carbon and the nucleophile that get departed simultaneously. So that in this reaction, since that occurs in a single step, there is no observable intermediate but only a hypothetical transition state. It that the carbon which is attached to 5 atoms or groups. This is very rare in all other types of mechanisms. Only in this type of, that means the bimolecular mechanism, we could have a carbon atom having more than 4 bonds. That means 5 bonds are here. So when the bond between that carbon and that nucleophile Br minus, here Br minus is the nucleophile, if it is completely formed at the same time, the bond between the carbon, in this example chlorine is the nucleofuge, that get completely cleaved off, so that the product is formed. Since the nucleophile approaches the carbon atom from the right side, there is a kind of inversion occurs, that what discussed under Walden inversion. So like an umbrella turning inside out in the while in a windstorm, here also inversion is possible. Suppose if you have started with a compound having R configuration, then the product definitely would have a S configuration. So S configured product will be formed. So this type of inversion is possible in case of bimolecular mechanism. Evidence for bimolecular mechanism: since this reaction is occurring in a single step, both the species are involved in the rate determining step. That means both the substrate as well as the attacking species. Most often by bimolecular mechanism, base acts as the nucleophile. So base is a must for a bimolecular mechanism to occur. So in this case, the R of the reaction is found to be 2. Rate of the reaction purely depends on the concentration of the substrate as well as the attacking species. Another important evidence for this, there is no designable intermediate, that means observable intermediate, only a hypothetical transition state is expected. And the stereochemistry of the reaction, as we have discussed in the previous slide, inversion in configuration, that means the compound will definitely have opposite configuration from the starting material. Another important mechanism in case of aliphatic nucleophilic substitution, but that is very rare. That mechanism is SNI mechanism, substitution nucleophilic, that occurs internally. In this given example RXY, that means the part of the leaving group that get detached itself and that acts as the nucleophile that get attached with the substrate, that means a carbocation, that means the incipient carbocation which is going to be formed will be attacked by the part of the leaving group, so that a new bond between that R and Y is formed. That X, that is called as the nucleophile, that is removed, that is the leaving group here. One of the best example for SNI mechanism is alkyl chlorosulfates are undergoing this type of mechanism. The chlorine atom in this case that departs. Actually that SO2Cl, that is the leaving group. So part of the leaving group is the Cl minus that get detached itself from the sulfur atom, and then it get introduced into that incipient carbocation, that means the carbocation which is going to be formed, that get attacked by that Cl minus ion, so that a new compound RCl will be formed. Actually that incoming group, that means the attacking species chlorine minus, since it departs only from that leaving group, there is only one chance for that nucleophile to attack, so that here that attack is always from the front side. So what would be the configuration? Definitely a retention in configuration. That means the starting material is having R configuration, means definitely the final product is also found to have R configuration only, since the configuration is retained here. The next major important substitution reaction is aromatic electrophilic substitution reactions. In the previous slides, we have discussed that aliphatic substrates are undergoing nucleophilic substitution reaction much easily. Like that, substitution at aromatic substrates are mostly electrophilic because the high electron density, the aromatic ring that attracts the positive species and not the negative one. In electrophilic substitution, the attacking species is a positive ion or a positive end of a dipole, or most often it may be a neutral species also. Unlike nucleophilic substitution, majority of electrophilic aromatic substitution proceed just by one mechanism. In this mechanism, the electrophilic attack in the first step that gives a positively charged intermediate, which we often call as rhenium ion intermediate, then the leaving group departs. That is in the second step, the rhenium ion mechanism. Almost all the electrophilic substitution reactions that occurs via only one intermediate, that is rhenium ion intermediate. In the rhenium ion mechanism, the attacking species may produce in various ways. In all the aromatic electrophilic substitution reactions, the first step is always generation of electrophile. So the electrophile, if it is a positive ion, it attacks the ring, removing a pair of electron from the sextate to give you a carbocation, which is a resonance hybrid as shown in 1 and is represented by 2 as a resonance hybrid. That 2 is a resonance hybrid. Like this. So in this mechanism, the first step is attacked by that electrophile, the positively charged species that attacks just by forming the bond with that carbon atom which is having the leaving group. Then since this electron which is common to the first and the second carbon atom, that electron is used for the bond formation with that electrophile. That electrophile that comes with only a vacant orbital, so that these two electrons are used for the formation of that bond. So after the formation of that bond, a positive charge is created on the second carbon atom that is stabilized by means of resonance. This is found to be the resonance hybrid of that intermediate. Since a sigma bond is formed between that aromatic compound and then the electrophile, these systems that can also be called as sigma complex. In most of the cases that can also be called as pi complex. That intermediate can also be called as Wieland intermediate. That means this is named after the scientist who discovered this intermediate. So Wieland intermediate. Ions of the type 2, that means the Wieland intermediate or the rhenium ion intermediate, are also called as sigma complex or rhenium ions. It is seen from the structure represented as in 1. The great stability associated with an aromatic sextet is no longer present in the resonance hybrid, that means the Wieland intermediate. Though it is stabilized by resonance of its own, the rhenium ion is generally a highly reactive intermediate and must stabilize itself by undergoing a further reaction. The most likely way is by the loss of either X minus or Y minus. X plus or Y plus. The aromatic sextet is then restored, and in fact this is the second step of the mechanism. The second step is always faster than the first step. So the first step is the rate determining step and the reaction is second order, as the two species, that means the substrate as well as the attacking species, are involved in the rate determining step. The R of the reaction and molecularity of the reaction are found to be 2. If X is lost, an aromatic substitution has not taken place. So if Y plus is removed, the net reaction, there is no net reaction. Suppose if X is lost, X is always, in case of aromatic substrate, is found to be a proton only. So the last step is always the removal of proton from that aromatic ring. Evidence for that rhenium ion mechanism: if the hydrogen ion departs before the arrival of the electrophile, or if the arrival and departure are simultaneous, there should be a substantial isotopic effect. But in the rhenium ion mechanism, the CH bond is not being broken in the rate determining step, so there is no net isokinetic effect. Isolation of rhenium ion intermediate is another evidence for the rhenium ion mechanism. For the reaction between the trimethyl compound number 3 and then ethyl fluoroborate, maintaining the conditions below minus 80 degrees Celsius, a rhenium ion intermediate which is produced, that is 4, that can easily be isolated, but the temperature has to be maintained below minus 80 degrees Celsius. That is the another evidence for that reactions, aromatic electrophilic substitution reactions, are proceeding through that rhenium ion intermediate. Ortho-para ratio: the proportion of the product formed ortho or para isomer is an electrophilic substitution depends greatly on the reaction conditions. For example, chlorination of toluene gives an ortho-para ratio anywhere from 62.38 to 34.66. On a pure statistical basis, there would be 67% of ortho and 33% of the para, since there are 2 ortho and only one para position. Here there are 2 ortho positions and there is only 1 para position. This would mean more than 33% of para and less than 67% of ortho substitution would be formed. A steric effect that plays also a major role in the rhenium ion mechanism. If either the group and the ring or the attacking group is larger, then the steric hindrance that inhibits the formation of ortho product, because both the ortho positions are sterically crowded, means then there is only one chance, then the para substitution that more probably occur. So ortho product and increases the amount of para isomer. An example can be nitration of toluene and tertiary butyl benzene under identical conditions. The former gave, that means nitration of toluene, that gives only 58% of the ortho isomer and 37% of the para isomer, while the latter, that means the tertiary butyl benzene, that gives 67% of the ortho isomer and 73% of para isomer. That means the tertiary butyl group that is very bulky in size. And so because of that, steric crowdness that plays a major role in directing the incoming group to the para position. orientation in benzene with more than one substituents. Substituents that is already present in the benzene ring can direct the incoming group either to the ortho position or to the some cases meta position or to the meta, most often to the para positions. Suppose if the groups already present in that system is found to be an electron withdrawing groups, then that directs that incoming group to the meta position. This is because both the ortho position will found to be slightly electron deficient because of the presence of electron withdrawing groups, and also the electron density and the para position that also be reduced, so that the incoming group will be introduced into that beta position. That means directed to the meta position. But if the groups already present on that benzene system, benzenide system, are electron releasing groups that are found to be the enhancing group in case of electrophilic substitution reactions, that will direct the incoming group either towards that ortho position or towards the para position, depending upon the nature of the groups already present. If it is bulky enough, then the para position is found to be very high when compared to the ortho products. But if more than one substituent is present on a benzene ring, normally they reinforce the case. For example, 1,3-dimethylbenzene, number 1, the structure 1 or A is substituted at the 4th position, since it is ortho to the 1, this position. For this case, this is ortho to this methyl group and para to this methyl group. But in the 5th position, which is meta to both the groups, for the case C, there is no reaction. Electrophilic substitution, under that the nitration is very important one. So in case of nitration, formation of that nitronium ion intermediate is the first step. So introduction of nitro group in the aromatic ring system is called as nitration. So mechanism of nitration that involves actual mechanism that involves only 2 steps, but in all those cases the generation of the electrophile, that is the first step. So actually considering the rate determining step is the second step. So mechanism of nitration that involves actually the 2 steps. The first step, that means attack by that electrophile NO2 plus is considered as the first step. Thereby it forms a sigma complex with that NO2 plus ions, and which on resonance stabilization forms a resonance hybrid, and the first step is the second step. In that second step, always removal of your proton, deprotonation is the final step in all the mechanism, in all the electrophilic substitution reactions. If proton is the leaving group, if there is no other substituents are found to be present, means proton is always the leaving group. This is how nitrobenzene is produced. Halogenation, in case of nitration, that NO2 plus, that means electrophile which is electron deficient. The best example for electron deficient species that acts as the electrophile. The second one, halogenation. So in this case, the bromine is that attacking species. That means an electrophile here is the dipole, the positive end of the dipole that acts as the electrophile. Then it forms a sigma complex. If it forms bond with that pi sextet, then that become a pi complex. Afterwards, by means of resonance, in case of electrophile, there is a positive end of that dipole, means pi complex is the most favorable pathway. Then that loses that proton, then that forms the expected bromobenzene as the final product. That bromination mechanism that can also occur in another pathway. That means Br plus can itself act as a electrophile. In that case, that mechanism that follows only that rhenium ion mechanism. That means a sigma complex is the favorable pathway. But that electrophile is a positive part of that dipole means in that case pi complex will be the favorable pathway. Formation of pi complex is the favorable pathway. The next mechanism is sulfonation. This is very good evidence or very good example for the that means a neutral species acting as electrophile. In these cases, sulfur trioxide as the attacking species, fuming sulfuric acid is the required reagent for the sulfonation reactions. So, introduction of sulfonic group in aromatic system is called as sulfonation. Actually, the attacking species is only the sulfur trioxide. So, after the attack by the sulfur trioxide, as we have seen in the previous mechanisms, a pi complex or even a sigma complex, since this is a neutral species, a pi complex is formed. So, after the loss of a proton atom or the departure of the proton from that substituted carbon atom, benzene sulfonic acid, the desired product, will be formed. The next major important mechanism, aromatic nucleophilic substitution reactions. In order to understand the concept of aromatic nucleophilic substitution reactions, one should know thorough idea or should have thorough idea about the aliphatic nucleophilic substitution reactions and aromatic electrophilic substitution reactions. Aromatic substrates, just now we have discussed that aromatic electrophilic substitutions are more favorable when compared to aromatic nucleophilic substitution reaction. This is because aromatic substrates are having the pi sextet that is easily available for the bond formation. That means that they are easily available for the donation, since in case of electrophilic substitution, electrophiles that comes with only vacant orbital, since electrons are easily available in case of aromatic substrate, that can easily form bond with that aromatic sextet. But for nucleophilic substitution, for a nucleophile to attack, a carbocation is required. That means a nucleus has to be generated first for a nucleophile to attack. But aromatic substrates are electron rich species. So, nucleophilic substitution on aromatic substrate somewhat tough to conduct. So, reactions that are successful at aromatic substrate that can be discussed in three different substitution mechanisms. A bimolecular mechanism that is discussed under the topic of SN-AR mechanism, a normal aliphatic mechanism like there is a unimolecular mechanism, that is SN1 mechanism. The third category, arine mechanism. SN-AR mechanism, that means bimolecular mechanism. The most important aromatic nucleophilic substitution, usually the first step is the slow and rate determining step, but not always. That means in all the cases of bimolecular mechanism, the first step is the rate determining step. Unlike our normal SN2 mechanism, in this case, this reaction that occurs in two steps. But in case of aliphatic nucleophilic bimolecular mechanism, that reactions that occurs in a single step. But here, this reaction that occurs in two steps like the SN1 mechanism. So, the first step here is the attack by the nucleophile, and that is found to be the rate determining step. So, order of the reaction and molecularity of the reactions are found to be 2. So, in the second step only, the leaving group, that means the nucleofuge that departs. So, the nucleophilic substituted product is obtained in the second step, that is the first step. Evidences for SN-AR mechanism. This mechanism greatly resembles the tetrahedral mechanism and also the rhenium ion mechanism of aromatic electrophilic substitution reactions. In all these cases, the attacking species forms a bond with the substrate giving an intermediate. Even in case of the tetrahedral mechanism, in the rhenium ion mechanism, just now we have discussed, in all those cases the attacking species attacks and then it forms the intermediate. Like that, in case of SN-AR mechanism also, after the attack by that nucleophile, an intermediate of this type is produced. Since this is sp3 hybridized, this resembles the tetrahedral mechanism. of aliphatic substrates. So this mechanism is generally found where there is activating groups, that means electron withdrawing groups are found to be present on the ring. Then only a nucleus can easily be generated. X-ray crystallographic studies proved that the structures of these intermediates and also studies on the effect of leaving group on the reaction gives more evidence. If the mechanism were similar to either SN1 mechanism or SN2 mechanism of aliphatic substrate, the ARX bond that would have been broken in the remaining step. But in the SN-AR mechanism, the bond is not being broken in the remaining step. Therefore, one could predict that this SN-AR mechanism is operating. That means SN-AR mechanism is quite different from the normal unimolecular mechanism of aliphatic substrate and bimolecular mechanism of aliphatic substrate. This is because this SN-AR mechanism that occurs in two steps similar to our unimolecular mechanism, SN1 mechanism that is operating in aliphatic substrate. But the molecularity of the reaction is found to be 2 like the bimolecular mechanism of SN2 reactions. That's why this mechanism is called as SN-AR mechanism, since this is completely different from SN1 and SN2 mechanisms of aliphatic substrates. In case of SN-UR mechanism, the change in the leaving group should not have much effect on the reaction rate. The very fact that the fluoro is the leaving group among the halogen in most aromatic nucleophilic substitution is the good evidence that this mechanism is different from SN1 and SN2, where fluoro is the poorest leaving group of the halogens. In case of SN1 mechanism and SN2 mechanism of aliphatic substrate, the poorest leaving group is always found to be the fluorine only. But here there is the best leaving group. This shows that this mechanism is completely different from SN1 and SN2, and there is an elemental effect. The most convincing evidence was the isolation of the intermediate of this reaction between the ethyl picrate and then methoxide ion. This forms an intermediate of this type. This intermediate was isolated by the two scientists, Meisenheimer and Jackson. So this is named after the scientist Meisenheimer Jackson. This intermediate is called as Meisenheimer Jackson salts. These salts are separable. So this gives another evidence for SN-AR mechanism. A normal unimolecular mechanism that is also operating in case of aromatic substrates. But for a unimolecular mechanism to occur in case of aromatic substrate, some activating groups are required. Activating group in the sense here, electron withdrawing groups are required. Most often, a unimolecular mechanism that occurs in case of aryl triflate or in case of benzene diazonium salts that also undergoing a unimolecular mechanism. So in this case, the given example, benzene diazonium chloride, in the first step, as in the case of SN1 mechanism, that undergoes ionization. That means the departure of that diazonium salt, decomposition of the diazonium salt that occurs and produces the cation, that carbocation that is attacked by the nucleophile in the second step. So since in the first step only one species, that means only one of the reacting species is involved, and that is found to be the remaining step, the molecularity as well as order of the reaction is found to be unity. Evidences for SN1 mechanism. The reaction rate is first order with respect to the diazonium salt and independent of the concentration of the added salt. If you are adding that externally, that Y minus, for example, any other species like Cl minus, if anything is added there, means there won't be any effect, because that is not the cleavage of that bond, that is not occurring In the first step, when high concentration of halide ion is added, the product is an aryl halide, but the rate is independent of the added salt. So the effect of ring substitution is inconsistent with the rate determining step. That means a high secondary isotopic effect is observed when the reaction is carried out with deuterated salt. This is because the CH bond, which is adjacent to that, that stabilizes that cation through a hyperconjugative effect. If a deuterium ion is introduced instead of that hydrogen ion, then the hyperconjugative effect that get diminished. So that stabilization through that hyperconjugative effect that get decreased. Then next important mechanism, the benzene mechanism. Usually for a nucleophilic substitution reactions to occur, activated substrates like aryl triflates or diazonium salts, that is very important. But some of the aryl halides are also found to undergoing nucleophilic substitution reactions. For example, chlorobenzene in presence of soda amide, that found to give two different products. Actually, if there is no labeled carbon, we couldn't able to find out whether actually two products formed or not. But if that leaving group bearing carbon that is labeled with the carbon 14, then after the substitution we can differentiate the two products. The one where that amino group is introduced on the labeled carbon, and the other case that amino group that is introduced and then carbon which is the next carbon atom. That means the carbon which is bearing the leaving group is not substituted. So this is possible only if the mechanism is operating through addition and elimination mechanism. Let's see the mechanism. This reaction also that occurs in two steps. The step 1 is found to be the pure elimination mechanism. In this case, that H and then this chlorine, the two are removed. That means the actual elimination process occurs, thereby an intermediate of this type is formed. A neutral species, a neutral intermediate is produced. At the second step only, the attacking species, actually ammonia. But for these reactions to occur, a strong basis like sodamide is required. Now this ammonia, that is the attacking species, that get introduced. But actual process here is NH2 minus that get introduced on one side of that multiple bond, and then the H plus is introduced on the other carbon atom. So that the net reaction is addition reaction. The second step is the addition reaction. First step is the elimination reaction. The intermediate which is produced during the first step of the reaction is called as a benzene intermediate. Only if the intermediate is a benzene intermediate, we can get two different products as we have seen in the case of chloro-substituted compounds. If both the ortho position is substituted, the reaction should not be able to occur. Another evidence for this is aromatic nucleophilic substitution occasionally results in substitution at different position. That means in the previous case, the two different products are obtained. Since that is mono-substituted, we can't differentiate. If it is labeled, that two substituted products can easily be discriminated. Substitution on this position and substitution at this position atom, at this carbon atom. Okay, so if the group is substituted at this carbon atom means, then that is called as sign substitution. That means substitution at different position. Sign substitution can be illustrated by the conversion of that orthobromoanisole to metabromoanisole. In this particular case, only the meta-isomer is formed. The reason for the formation of the meta-anisole is the intermediate 1. It's not symmetrical as we have seen in the previous case. Benzene intermediate that is symmetrical, so that can be attacked in both the position. But in this case, there is only one possibility. This intermediate is not symmetrical. So the group which is already found to be present is the methoxy group, that is electron donating group. So that the incoming group, that is NH2 minus, that approaches this carbon atom So this will be shifted here. So the product is found to be meta-anisidine and not that ortho-anisidine. So the group which is already found to be present on that system, that means the substrate, that plays a major role in directing the incoming groups. So this proves that sign substitution is occurring in this type of compounds, substitution reactions. Sign substitution is the one of the evidence that the mechanism which is operating is benzene mechanism. Thank you.